In previous lecture, we understand the restoring couple that is equal to WGM sin theta. So from here, the restoring couple will be WGM tan theta. So GM is the metacentric height. So how to calculate this metacentric height? So there is a process that is measurement of metacentric height. So how to calculate the metacentric height? So metacentric height can be measured by two methods. One, experimental method. Two, analytical method. So first focus on the analytical method. In this method, the metacentric radius is defined in terms of geometric condition of floating body, that is moment of inertia of waterline area and volume of fluid displaced. Okay, so restoring couple, that is we know that the formula, that is WGM tan theta. W is the weight of the body, GM is the metacentric height, and tan theta the tilted angle theta. So this theta is from range 0 to 90 degree. So for that, tan theta will be greater than 0, and W is always positive and tan theta positive. So there is a metacentric height. So GM. If GM greater than 0, there is three cases there. If GM greater than 0, that is positive restoring couple, and it is also known as stable equilibrium. Now if GM less than 0, that is the negative restoring couple, and it is also known as unstable equilibrium. And if the GM, that is the metacentric height, that is equal to 0, that is known as zero restoring couple or neutral equilibrium. So this is all about the GM concept for stable, unstable, and neutral equilibrium. Now GM for metacentric height, if you want to, for metacentric height, there is a experimental method is there to calculate the metacentric height, and there is a analytical method are there. So experimental method, which is used after design, and analytical method, which is used at the time of design. Okay, so suppose this is sieve is there, this is one sieve, and on that sieve there is one body is there, and weight of the body, that is mg. Now if the body is displaced from this position to this position at x displacement, so the mg is acting in that position. So applied couple, what will be the applied couple? That is equal to mgx. The applied couple, that is will be equal to mgx, and restoring couple, what is restoring couple? WGM tan theta. So for equilibrium condition, WGM tan theta, that is equal to mgx. So from here you can calculate the GM, that is equal to mgx by W tan theta. So this is the formula for find out the metacentric height. Now if we focus on the analytical method, so analytical method, which is used at the time of design. So suppose this is the metacenter here, metacentric point here, this is the metacentric point M, this is the centroid of the body, and this is the center of buoyancy. So B is center of buoyancy and G is the centroid of the body. So from here to here, that is the distance, that is G into M, sorry, GM. This is the height. So what is GM? GM is the metacentric height. And from here to here, the distance is BG. Okay, BG. Now from here to here, the distance is BM. Now what is the relation between GM, BM and BG? So GM, so this height, that is equal to BM minus BG. So you can say that BM, that is equal to GM plus BG. Okay, so this height, this total height equal to this height plus this height. So from here, GM, that is equal to BM minus BG. Now the case is that when GM greater than 0, that means BM is greater than BG. For that case, this is known as stable equilibrium. And if GM less than 0, when it is possible? When BM less than BG. So this is known as unstable equilibrium. And GM equal to 0, this is for neutral equilibrium. It is possible only when BM, that is equal to BG. So GM is the metacentric height and BM is the metacentric radius. Now for analytical method, if we focus on the analytical method, so here this is one sieve is there. So this is the front view of the sieve, and this is the metacenter point, and sorry, this is the center of buoyancy, and this is the centroid of the body. Now this is the free surface here. So this is the free surface, and the sieve upper area, the length of this sieve, that is D, and width, that is B. Okay. Now we know that GM, that is equal to BM minus BG. This formula, from this formula, GM, that is equal to BM minus BG. So just so here this is the cross section here. So D is the length of the sieve and B is the width of the sieve. Now if the sieve will rotate in this axis, So this is known as rolling, and if it is rotated in this axis about this axis, this is known as pitching. Remember this point, very very important. Now if you know this is the volume here, this area into perpendicular distance, this is the VFD. VFD is the volume of the fluid displaced or discharged. Okay, so now BM, there is a formula, that is BM, that is equal to I by VFD. So VFD, that is the volume of the fluid displaced. Okay, so VFD, that is volume of the fluid displaced. I is the least moment of inertia of waterline area about tilting axis. So this is the I is the least moment of inertia of waterline area about tilting axis. So the case is there. Now for rolling, so if you want to calculate for rolling case, I of rolling, that is equal to d beer cube by 12. So if you want to calculate the moment of inertia about rolling axis, that will be d beer cube divided by 12. So d beer cube divided by 12. And if you want to calculate the moment of inertia about pitching axis, then that is will be b d cube by 12. So for pitching axis, there is a d, so this will be d cube, so b d cube divided by 12. For rolling, that is d b cube divided by 12. So this is the I rolling, that is equal to d b cube by 12. And for pitching, I of pitching, that is b d cube by 12. So in that case, b less than d. So from here you can say that I of rolling less than I of pitching, because d is greater than b. So for that case, I of rolling, because there is v cube is there. So I of rolling, that is greater than I of rolling, that is less than I of pitching. Okay, because d is larger, so there d is larger. So that's why this value will be greater than this value. So R rolling less than I pitching. So from here BM rolling less than BM pitching. So from here you can say that GM rolling less than GM pitching. Now suppose there is any shape of the body. This is the shape of the body here. Now this is the diameter, that is d, and the height of the body, that is h. Now up till this section the body is in the fluid. Now this is the free surface here. So from here to here the height is small h. So from here to this metacentric point, that is 3 by 4 into h, and from here to here the distance is 3 by 4 into capital H. Okay. Now if you want to calculate the moment of inertia I, that is pi by 64 d to the power 4. And how to calculate VFD? So VFD means this volume. So 1/3 pi d by 2 whole cube into h. Okay. Now if you want to calculate the BM, that is equal to I by VFD. So that is equal to, what is the value of I? That is pi by 64 d to the power 4 divided by 1 by 3 pi d cube by 8 into h. So this value. So if you calculate these things, so from here BM, that is will be equal to 3d by 8h. So this is the concept here. Now there is another concept, that suppose there is one ball is there, and this is the free surface here. Now this is the center of buoyancy point, and this is the center of gravity where the weight is acting from here, and this is the center of buoyancy. Now for ball, the restoring couple will be 0. Okay, GM is equal to BM equal to so restoring couple equal to 0 means BM, that is equal to BG. So here there is a restoring couple, that is 0. So it is known as neutral equilibrium. Now there is one question that is important, that is assertion: a floating body of spherical shape shall always be in neutral equilibrium condition. Reason: for a spherical floating body, the center of gravity is always above the center of buoyancy. So A and B both statements are correct, but R is not the correct explanation of A. So the answer will be B. So this is very very important for ESC, Engineering Service Examination exam. So now we'll understand the next important question, that is very very important for GATE point of view. So a cylindrical body of cross section area A, height h and density rho s is immersed to a depth h in a liquid of density rho and tied to the bottom with a string. The tension in the string is, so you have to find the tension of the string. So what is given in this question? So there is one case is there. There is up till this there is a fluid there. Okay, so the body height, that is h, capital H, and from the free surface to this here the height is small h. Okay, now the buoyancy force which is acting upward direction and the weight of the body which is acting downward direction. So and there is a string which is tied to the bottom with a string. So here there is a tension which is acting downward direction. So So how to calculate the buoyancy force? Buoyancy force, that is omega F VFD. Omega F, that is specific weight of the fluid. So how to calculate specific weight? That is rho F into G. Rho F, the density of the fluid, G is the gravitational acceleration, A is the area and height. Area means this area into height. Okay, so area into height. So area is given, so here the area is given and multiplied by this height, so you can find out the VFD. Now if you want to calculate the weight of the body, that is specific weight of the body into volume of the body. So rho S, rho B, G into A into H. A is the area of the body and height of the body. Now here if you focus on that, here W is acting downward direction, T is also downward direction. So from here W plus T is equal to FB. So you can write in this way. So W plus T, that is equal to FB. So T, that is equal to FB minus W. Okay, so FB, just put the value here. FB, that is rho F G A into H, minus what is the value of W, that is rho S, or you can see that rho B. Okay, density of solid here, what is written, that is density of solid, rho S. So rho S G A into H. So from here A into G common, so rho F H minus rho S H. So this is will be our answer. Now if the question is given in this way, suppose up till that there is a fluid there, and here there is a body, and this is the free surface here. So body have the height here to here, this is H, capital H, and there is a oil up till here to here, there is a oil, and from here to here there is water is there. Okay, now oil height, so here to here the height is H1, and from here to here the height is H2, and W is acting downward direction, A is the area of cross section of the body, and there is tension which is acting downward direction, T. Now how to calculate for this case? How to calculate the tension for this case? There is two fluids there. So above case there is one fluid are there. So in that case there is two fluid are there. So how to calculate that? So if you want to calculate for oil, that is the bouncy force for oil, that is rho omega for oil into V0, V for oil. So omega into H into H1 into A. H1 is the height and A is the cross section area. And F of water, that is equal to omega of water, V of water. So omega of water, H2 this height into cross section area A. Now from here T is acting downward direction and W is acting downward direction, so T plus W, that is equal to buoyancy force which will always act upward direction, so F0 plus FW. So from here you can directly calculate the value of T, that is equal to F0 plus FW minus W. Okay, so this is the answer. Now one important question is there, assertion, most floating ships are more stable in pitching about transverse axis than in rolling about longitudinal axis. Reason, ships have greater length than width. So here A and B both statement, A and R both statement are correct, and R is the correct explanation of A. So answer will be A. This is very important question for ESC point of view. This is my handwritten notes. You can download it from the description. The PDF link is available on the description. If you have any doubt, you can directly comment me. Like, share and subscribe my YouTube channel. Thank you.